In this presentation, I will talk about our recent project on reliable semi-supervised learning via prediction-powered inference. I am a postdoc at King's College London, and this is a joint work with Professor Osvaldo Simeoni. So let me start by the context and motivation of this work. So as you know, next generation wireless systems will rely extensively on machine learning and data-driven decision making. However, in many scenarios, labeled data is costly, while unlabeled samples are abundant. For instance, in wireless systems, labeling may require costly optimization or data collection campaigns via on-air transmissions. So, acquiring labeled data in wireless networks faces many challenges, such as it is time and energy consuming. Moreover, the wireless communication environments are dynamic, so we need to collect new data each time the environment is changing. There is also another challenge related to privacy concerns. So, semi-supervised learning via pseudo-labeling provides a promising alternative by leveraging synthetic labels produced by machine learning models. So, pseudo-labeling is basically consists of training a teacher model using the available labeled data, and then use the teacher model to provide pseudo-labels using the unlabeled data, and then our target model, or usually called student model, can be trained using both the labeled and unlabeled data. Moreover, digital twins can be leveraged along with these semi-supervised learning schemes in order to enhance the performance of machine learning models in wireless communication systems. For instance, digital twins can help to acquire unlabeled data. So, for instance, in many applications, we can sample receiver location from the coverage map of transmitter, and this can be valuable in many applications. For instance, as we will see later, for it can be important for beam alignment via channel knowledge map. Moreover, digital twins can help to produce synthetic labels. So, for instance, as we have seen in the previous talk, the ray tracing techniques can be used in order to estimate the channel matrix, and then this can be used in order to do beamforming, for instance. So let me present the context of this work. So we assume that we have a labeled data set and then a much bigger unlabeled data set. So we assume, moreover, that we have a teacher model, a pre-trained predictor, and we want to estimate a parameter vector that minimizes our population loss. So the classical way is to use just the labeled data and determine the optimal parameter vector that minimizes the empirical risk loss. Another way is to use classical semi-supervised learning techniques that are based on pseudo-labeling, where we use the predictor to get pseudo-labels and then combine both the labeled and unlabeled data in order to optimize our parameter vector. However, this may lead to some bias because the predictor model can be biased in practice. So that's why this conventional semi-supervised learning schemes can have poor performance in practice in many scenarios. So recently, this work presented the prediction-powered inference, which is a framework that allows the use of a pre-trained machine learning model in order to provide pseudo-labels while taking into account the possible bias of these prediction models. The idea is, instead of using just the unlabeled data when estimating the optimal parameter vector, we want to remove the bias of the prediction model by and this bias is estimating using this term. So this this loss is unbiased, and the PPI estimator will have lower variance than the classical ERM estimator when the number of data points in the unlabeled data is much bigger than the number of data points in the labeled data, and when the predictor F is sufficiently accurate. However, in practice, the model F is not always accurate. So the work here in this reference, efficient prediction powered inference, proposed to tuned PPI, where they introduced a tuning parameter in the PPI loss in order to adapt depending on the quality of the prediction model F. So basically, we want our tuning parameter to converge to 1 when the model is sufficiently accurate, and to converge to 0 when the pseudo labels are not perfect. So, and these tuning parameters can be optimized, which yields a data-dependent parameter that reflects the accuracy of the model F. So both PPI and tuned PPI assume a pre-trained model, but this is not the case in practice. So cross-prediction powered inference is proposed in order to alleviate this assumption. So it consists of partitioning the available labeled data into K faults, and then K prediction models are trained using this labeled data. So each prediction model is training or using all the labeled data except one fault, which will be then used in order to estimate the prediction bias of this model FK. So it's the same idea as PPI, but here we will use all the available data in order to train K prediction models. Of course, in practice, these machine learning models are not always sufficiently accurate. So we propose in this work to use a tuning parameter that allows the flexibility to adapt the use of unlabeled data as a function of the quality of these trained models. So the optimal tuning parameter can be then chosen in a way to minimize the mean squared error of our tuned CPPI estimator. So in order to determine the optimal parameter lambda, we need to conduct the asymptotic convergence analysis of our proposed estimator. And by doing so, we have shown that the difference between the tuned CPPI estimator and the optimal parameter theta star converges in distribution to a Gaussian with zero mean and a covariance matrix sigma lambda given by this equation. So, and then we can optimize lambda in order to minimize the variance of our estimator, or basically to minimize the trace of the covariance matrix sigma lambda. So the optimal parameter that minimizes this mean squared error is given by this equation, and this can be estimated in practice by replacing these quantities by their empirical estimates using both the labeled and unlabeled data. So till now we have assumed that the population loss is convex in theta in the parameter vector in order to guarantee this theoretical analysis of the PPI and tuned PPI estimators, but in practice they can be used with non-convex losses. And we have tried tuned CPPI with deep neural networks, and it has better results than just using classical semi-supervised learning techniques. So the idea is to introduce some parameter that allows to the gradual introduction of labeled data in the loss in order to avoid numerical instabilities. Then we have tried to combine the tuned CPPI estimator with more recent pseudo-labeling technique. For instance, we have considering meta pseudo-labeling, which is one of the state-of-the-art semi-supervised learning techniques, that allows the use of labeled and unlabeled data. So the idea of MPL is to train the teacher model alongside the student model. So at every iteration, we do a gradient step on the teacher model and a gradient step on the student model. The loss of the teacher model depends on the labeled data, and another term that reflects the performance of the student model on the labeled data, and the student model uses the pseudo labels provided by the teacher model at each step. So tuned CPPI can be combined with MPL in the following way. So instead of having just one teacher model, we have K teacher models that are trained alongside the student model. And the student model will use, in this case, the tuned CPPI loss in order to account for the potential bias of these teacher models. So we considered one application of this in wireless communication systems, specifically beam alignment via channel knowledge map in massive MIMO systems. So channel knowledge map is a site-specific database of channel information that is linked to transmitter and receiver location. So for instance, this channel knowledge map can be the location of the users and the channel gain of that is obtained at these locations from a given base station. So each base station or each collection of base stations can have their own channel knowledge map. So channel knowledge map can simplify the acquisition of real-time CSI and potentially eliminating the need for explicit training in some applications. So specifically, the system model consists of the downlink of millimeter wave massive MIMO systems. We want to determine the optimal beamforming vectors at the base station and the UE. And these beamforming vectors are chosen from finite code books. So we want to select the best beams given the location of the user. So by exploiting the channel knowledge map. So the idea here is to augment the available data in the channel knowledge map using semi-supervised learning techniques. So the labeled data set consists of channel knowledge map and samples with here xi is the location of the user and zi is the path information. The unlabeled data set consists of some new locations in the coverage map of the base station. This can be sampled, for example, from a coverage map, which can be estimated using ray tracing techniques. So we want to answer the following question: how would this PPI variants, including the proposed tuned CPPI, enhance the performance by leveraging the unlabeled data? So our benchmark schemes are the classical ERM, which uses only the labeled data, conventional semi-supervised learning techniques that treats synthetic label as true labels, the other PPI variants, and meetup pseudo-labeling. So here we plot the channel capacity as a function of the number of station antennas, and of course these models are used to predict the optimal beamforming vectors. So we can see that the proposed tuned CPPI provides better performance than the benchmark schemes, so all the other PPI schemes. And we can see that classical semi-supervised learning techniques fail to provide any gain compared to just using the labeled data. So here we see the same behavior. So the proposed tuned CPPI outperforms or other PPI schemes. So here some results with deep neural networks. So we see the same behavior. So tuned CPPI outperform all other PPI schemes and has significant gain compared to just using the labeled data or using classical semi-supervised learning techniques. So in this figure, we compare with the MPL. So here we plot the performance of classical CPPI, the proposed tuned CPPI, MPL, and meta CPPI, which is the combination of MPL and tuned CPPI. We can see that MPL is able to outperform the classical tuned CPPI and CPPI, and this is expected because MPL is training the teacher model, keeps training the teacher model alongside the student model, while tuned CPPI, for instance, just train the teacher model once and then use it for labeling the unlabeled dataset. However, when we combine the tuned CPPI approach with MPL, we can enhance even the performance of MPL. So in this presentation, we have seen how we can use the PPI framework in some application scenarios in wireless systems. We have proposed a new variant of PPI, which is tuned CPPI, that is shown to guarantee the best performance compared to other PPI schemes. And we have shown how tuned CPPI can be combined with recent pseudo-labeling schemes such as MPL to provide even better results. So this work can be extended by identifying and studying other application scenarios of the PPI framework in wireless communication systems, and also by studying the effect of distributional shift on the performance of this prediction-powered inference schemes. Yeah, that's it. Thank you very much.